Hello folks, we're back with more line integrals. Today we're going to go into flow and flux. This is very similar in terms of the formulas involved with the work integrals, but instead of a force field, now we're going to concentrate on velocity fields. So what you can imagine this as basically some kind of fluid moving in some region in space, okay? And at each point we know the speed and the direction of the fluid. So that's what we think about today's velocity fields. They're going to represent the motion of a fluid, okay? The velocity field of a fluid, maybe a gas, okay? If you're in three-dimensional space. Today we're gonna be on the plane most of the time. So it's gonna be, let's say, a fluid, okay? And we'd like to do is we're going to calculate the flow and the flux. Okay, so these are nice vocabulary words, right? Funky vocabulary words. So let's try to understand what we have. So given a curve, let's say we have a curve, and we'd like to find we have some kind of velocity field, maybe like this. I don't know, something crazy going on like this. Okay, and we have a curve in space like this, C, okay? So when this curve is smooth, I'm trying to figure out how much fluid is flowing around, flowing along this curve, okay? Along how much fluid is flowing along this curve. So that's basically the same problem as the work problem, right? We are only going to care about the tangential component of the fluid, of the velocity field along the curve. So it's just like the work integral, but this time when you have a velocity field, it's called the flow. Okay, flow along the curve C, where is the integral f dot product, it's not times, it's f dot product t ds. In other words, the tangential component of f along t, okay, ds. Now, because it's exact, formula-wise, it's exactly the same thing as the work integral, we already know the formulas of how to evaluate this, okay? So remember, we derived a whole bunch of formulas last time on how to evaluate integrals of f dot product t ds, and it's going to be the same stuff. So instead of the work, when you have a velocity field, it's the flow. Okay, so another thing that we'd like to do today is we're going to be mostly interested in closed curves. Okay, so we're going to think about maybe we have a closed curve like this. Okay, we want it to be smooth. We want it to have continuous derivatives. Okay, we want it to be smooth. When we have a closed curve, we call it a loop. Okay, so a loop is just a closed curve. It doesn't have to be symmetric or anything like that. It's just a closed curve. Okay, and the other question we can ask is, well, there's the flow along the curve, but what about if you have a velocity field like this, something crazy, what about the flow across the curve? Okay, the flow across the curve. So how much water crosses this borderline? So think about all the fountains you might have seen. You know, they're very nice fountains with nice fantastic shapes, maybe flower shapes or something like that, and water is sprouting in the middle, okay, and then the water is flowing. So I'm just wondering, if it's raised a little bit, how much water crosses this boundary, okay, the boundary of C. So in that case, so the difference between flux and flow is how much water flows along the curve. Flux is how much crosses the curve. Okay, so the word flux is how much water closes a closed loop. That's a closed curve, which is a loop. Okay. So again, we want the same kind of setup. We're gonna have a continuous velocity field. Okay, a vector field basically. And we're going to have this time a simple smooth loop. Okay, simple means it doesn't cross itself. So this would be simple. Okay, this would be simple. This would not be simple. If it crosses itself, it's not simple. Okay. Okay, so when you have a simple curve, okay, well, we want to, and we want it to be smooth. It's got continuous derivatives. It's a very nice curve, and we have a continuous vector field, a velocity field. We want to calculate the amount of fluid leaving this region. Okay, going across the boundary. So, so the way we're going to set it up here is, again, f is going to be equal to mi plus nj. Remember, we talked about this last time. M and n are not constants. These are two variable functions in this case, okay? Because we're talking about flow across a loop, okay, we're in the space, two space. We're not in three-dimensional space. We're in two-dimensional space. So we got two components, okay, for the continuous force, continuous velocity field. And we have some simple smooth loop in the plane, okay? Then to calculate, of course, to calculate the amount of stuff leaving this, right? We need to figure out the normal component, okay? The normal component of the force along this curve, okay? What's the normal component? Because, you know, only the normal component, when you have, let's say, a vector like this, only the normal component of it is going to contribute to the stuff that's leaving on it, okay? So we want to find the normal component. So what we're going to do is f dot n ds. Guys, this n here is the normal vector, okay? The normal vector, vector pointing out, okay, pointing out on the boundary across C, and that's going to give us the flux, the amount of stuff that's leaving that region. So how are we going to evaluate this? Okay, so this makes sense. The other one was f dot t. Again, t was a unit tangent vector. This one is f dot n. This is the unit normal vector, okay, ds. Now, remember, when we were doing the f dot t, the flow integral or the circulation integral. Oh, guys, I forgot to say something. This flow integral, if the curve is closed, it's called the circulation. Okay, so flow so if the curve is not closed, flow along this would be just flow. If the curve is closed, flow along this loop would be called circulation. Okay, so they're just the same thing. One is closed, okay, one is not. So when you compare these, the way to remember this is along you need to have f dot ts. T is the unit tangent vector, and across the flux you need to have f dot n is the unit normal vector that's pointing out. So we need to get back to calculating, evaluating these integrals. How are we going to set these integrals and evaluate them? So we have to figure out, okay, I know how to get the tangent vector, right? That's just dr dt. But how do you get the normal vector? So what we're going to do is here we have to be very careful because the orientation that we describe the curve C with matters. So let's say we're describing the curve, okay, as a vector valued function. We have r of t is gti plus htj, okay? So g of t, h of t, we're describing it in terms of time. Now, remember this, every single parameterization gives us an orientation, a way we travel along the curve. If our orientation is counterclockwise, okay, we're going around like this, okay, then I can calculate, I can get the tangent vector, no problem. The tangent vector is just dr dt. And the vector k, when I say the vector k, I'm talking about the vector k, the one that's along the z-axis. If I take the cross product tk, okay, t is this way, k is up, okay, so I'm going to point this way. It's going to get t cross k is going to give me the normal vector here pointing out. So n is going to be equal to t cross k when the orientation is counterclockwise. If, on the other hand, the orientation is clockwise, okay, so we're going around like this. This time the vector k coming out towards you guys, okay, and this is the tangent vector. Then what are we going to have? We need to have kt, so k t, and this way is going to be k cross t. So in one of them, okay, so the way you calculate the integral does not matter. The integral formula is exactly the same for both of them. But the formula for n changes, okay? In one of them, n is equal to t cross k. In the other one, n is equal to k cross t, okay? So today, we're always going to assume we're parameterizing curves counterclockwise, okay? Unless we say otherwise, unless I say otherwise, I'm always going to try to find parameterizations of the given curve in a counterclockwise method. So the way we're going to set this up is f and ds. We want to evaluate this. Now, because it's a closed curve, we put a circle around it. Because we're going to do counterclockwise, just to show that we're doing it counterclockwise, we put an arrow like this. If it was clockwise, we'd put an arrow the other way. That being said, in every single application in your calculus books that you're going to see, the curves are always going to be oriented counterclockwise. Okay, so if I forget to draw the arrow, you can assume it's counterclockwise. If for some reason the clockwise orientation is easier for us, the clockwise parameterization is easier for us, I'll explicitly say it and always put a direction, an arrow the other direction. Usually, 99% of the time, the way we're going to do is we're always going to try to find counterclockwise orientations of curves. Now, let's go back to the math involved. So f dot n ds, in that case, because we're doing counterclockwise, n is going to be equal to t cross k. Okay, t cross k. So that's going to be dx ds. Remember, tangent is the unit vector, so it's going to be dx ds, the arc length differential, dy ds, times cross product k. That's what we're trying to do. So what we're going to do is, well, I set it up here. Let's do the cross product, ijk, dx ds, dy ds. Well, the third component is just 0. And for this one, we have 0, 0, 1. And what is this going to be? Well, across here, we're going to have I times dy ds. This is going to be 0. This is going to be 0. This, on the backwards version, this is 0. This is 0. So we only have this one. So it's going to be minus j times dx ds. So I'm just doing the work here. We're going to end up with a very nice formula. So we have dy ds I minus dx dj, dx ds j. That's going to give me the normal vector. So moving on, let's plug it in. Okay, so I rewrote everything here so that we have it in front of our eyes. We want to calculate f dot dn. What was f? F was mi plus nj. So f dot n would be m comma n as the vector. And we already found what n was, right? N was equal to dy ds I minus dx ds. So I'm taking that dot product now. We're taking this dot product. Let's put a big fat dot over there. So what we end up with is we have m times dy ds, n times minus dx ds. Okay? So along the curve, along the closed loop C, we're going to have n dot ds is the same thing as along the curve m dot dy ds minus n dot dx ds times ds. Now, of course, because of the chain rule, where ds is the arc length differential, well, because of the chain rule, the ds's cancel each other out. So we have this formula. I don't know what it means yet, but we are drawing the integral along the loop, counterclockwise direction, m dy minus n dx. Okay, so this is basically the flux. Okay, this is the flux. This is the amount of stuff leaving the region. Now, having said that this is interesting because, okay, and again, we're going back to the last lecture, finding m dot dy. This is a function, two variable function. We take in the partial integral. You know, we can do this. This is calc 1 question, but what does it mean to evaluate around the curve? So we have to go back to the parameterization somehow. All right. We're going to do examples to show you exactly how that works out. So I picked a question from the book showing everything, the applications of this to an actual force, an actual velocity field. So what we'd like to do is we have find the flow and flux for when the velocity field is x minus yi plus xj. It's a very simple velocity field, nice velocity field. Okay. Across the curve, x squared plus y squared equals 1. Now, that's, of course, the unit circle, okay? So we have the unit circle. I tried to draw the vector field here. The first one is we want to find the circulation. I shouldn't say flow here. I should actually say circulation, right? It's a closed curve. So when it's a closed curve, flow is called circulation. So how much stuff circulates around the circle and how much stuff leaves the circle? That's what we want to calculate. All right, so if we set this up now, circulation was F dot product TDS, okay? But remember, that's not going to help us much. To evaluate this, what did we do last time? We turned this into parameterization. It would be F dot dr dt times dt, okay? That's how we calculated the last time. So what I'm going to need to do is I'm going to need to find dr dt. Now the curve in this circle, so a counterclockwise, the standard orientation is counterclockwise. What's the standard parameterization of the circle? It's cosine ti plus sine tj. Okay, and I rewrote the f over here, so we have it right in front of our eyes. It was x minus yi plus xj. So now we need to calculate dr dt because the formula is f dot dr dt dt. So dr dt is going to be minus sine ti plus cosine tj. Now, remember, we're getting our x. We're interested only along the curve. We're getting our x from here, and we're getting our y from here. So plug it in here for f, okay? This guy is going to be f. This guy is going to be dr dt. Okay, so plug it in. X is going to be cosine minus sine I plus cosine t. So as a vector notation, we can write cosine t minus sine t comma cosine t. And we already calculated dr dt. Guys, it's not t, it's dr dt minus sine t cosine t dt. Okay, so do the dot product. We're going to have minus cosine t sine t minus a minus sine squared. So it's going to be plus sine squared t. And then we get cosine squared t dt. Of course, this guy over here is 1. So what we actually have is 1 minus, I just reversed the order, 1 minus sine t cosine t dt. So integrate this, you get t minus, this is just a simple substitution, right? If you call this sine t u, this is just du, so it's just going to be u squared over 2. In other words, it's going to be sine squared over 2. Evaluate from 0 to 2 pi. Of course, this term is 0. You get 2 pi as the answer. So this is our circulation. Okay. Now let's go to the flow. Let's go to the flux. Let's go to the flux. So for the flux, instead of doing f dot t, we have to do f dot n, where n is the unit normal vector. Now, we already saw that we can write it as m times dy minus n times dx. But how am I going to calculate this? Well, the way I can do this is, well, I can do this n times dy dt times dt. They would have canceled this, each other out. Minus n times dx dt. Now, along the curve, okay, we go around the circle. I forgot to say this. T, of course, here is between 0 and 2 pi for the standard parameterization of the circle, right? Okay. So we go around the circle in 0 to 2 pi. So instead of dy, I can write m dy dt dt, 0 to 2 pi, minus, and instead of dx, I can write dx dt dt. Okay, so what was m? Remember, m was cosine t minus sine t. Okay, what is dy dt? Well, dy was equal to sine t here. So dy dt is going to be cosine t, okay, dt. Similarly, n was cosine t, because remember, it was just x, so it is just cosine t. And dx dt, well, the x was cosine t, so it's going to be minus sine t dt. So that's how you calculate, okay? You go back to t's, basically. You always go back to t's. Well, at least for now, we're always going to go back to t's. Okay, so once we do that, once we do the whole multiplication, I put the two integrals together. Let's see them one under another. Okay, so we had this integral on the previous page. So what's going to happen here is we're going to have a cosine squared minus sine t cosine t minus a minus, that's going to make it a plus, cosine t sine t. So these two guys, of course, are going to cancel each other out. Okay, I put them in a single integral. then we can move on. So we just have the integral from 0 to 2 pi of cosine squared t dt. Well, how do you do those? We have to use the identity cosine squared is equal to 1 plus cosine t over 2 dt. I pull the 1/2 out. Then we have the integral of 1 is going to be t. The integral of cosine t is, of course, going to be sine 2t over 2. 0 to 2 pi. Of course, this term is 0, so you get 2 pi over 2, which is pi, and this is the flux. Okay. So, again, what I'd like to say to you is, watching me or watching the examples in the book, it seems easy, but unless you get some exercise, of course, you're not going to be very good at it. You're going to get confused. You're probably going to confuse the formulas and whatnot. So I highly suggest open up any calculus book and do a few of these circulation and flux problems. So you get a handle on what's going on. Next time we're going to be back with more vector fields. Till then, take care. Bye-bye.